So in the last video, I think I said that we were going to be moving on to chapter 13. Well, I lied. There is one more tiny topic that we need to talk about before we move on to actually applying the Laplace transform to our circuit analysis. And that topic is poles and zeros. We're just going to jump right in, but basically poles and zeros are going to be really important when we start designing our frequency selective circuits, when we design, in this class, filters, and later when you move on to amplifiers. Doing the frequency response and then calculating the poles and the zeros are going to tell you an awful lot about how that circuit's going to respond to particular frequencies. So let's go ahead and dig in. Okay, so let's first talk about what poles and zeros are. Poles, for lack of a better explanation, is just a place where our Laplace transform, our function of s, goes to infinity. And a zero is just a place where our Laplace transform function of s goes to, you guessed it, to zero. And that's actually all there is to it. And as I said in the little intro, this will be really important for our filter circuits. We will we will analyze circuits and calculate their poles and zeros to figure out what their frequency response will be. And we'll also design our filter circuits to have specific poles and zeros in order to get the frequency response that we're looking for. Now, the way this works is pretty simple. You may have noticed that our Laplace transforms often take a pretty similar form. There's oftentimes some constant times a polynomial, a function that can be factored into what we'll call this, s plus z1, hint, hint, that's for zeros, plus s plus z2 times s plus z3, on and on forever. And they're usually over another expression that is also a polynomial, something that can be factored out to s plus p1, or times s plus p2 times s plus p3, and again on and on forever. Now the technique to find the zeros, so let's say we want to find the zeros, is pretty easy. We take this first polynomial expression, so let's just say s plus z1 times s plus z2 times s plus z3, and set it equal to 0 and solve for s. And wherever the function is equal to 0, whatever that s value is, that's what we're going to call our zeros. And the poles are exactly the same way. If we want to find the poles, we're just going to take that denominator, s plus p1, s plus p2, s plus p3, on, and set that equal to 0, and solve for s. And that value s in the denominator, that gives us 0 for our function, right? Remember, so anytime we're approaching 0 in the denominator, that's going to drive our function to infinity. So that's going to be our poles, our places where f of s is equal to infinity. And that's all there is to it. Let's go ahead and work out a couple of examples. So let's call this first one example 1. And in that example, they've given us that f of s is equal to 40 times s cubed plus 440 times s squared plus 2,200 times s plus 5,000 over 4 times s to the fourth plus 88 times s cubed plus 880 times s squared plus 4,000 times s. So let's go ahead and find the zeros first. So we'll take the numerator of f of s and set it equal to 0. So let's go ahead and say 40 times s cubed plus 440 times s squared plus 2,200 times s plus 5,000 is equal to 0. Now, I'm sure in your high school and college algebra classes, you learned techniques for solving these polynomials, but I'm going to choose for us to be lazy. And so what I recommend you do is you flip over to your calculator or your favorite numerical tool. My personal favorite is Wolfram Alpha, and go ahead and plug in those expressions there. So let's go ahead and say we want to solve the function 40 times s cubed plus 440 times s squared plus 2,200 times s plus 5,000, and we're going to solve for s, and that's going to give us our zeros. And there we have it. We get that. We have an s at minus 5, an s at minus 3, minus 4i. Remember, Wolfram Alpha is going to use i's for the complex number. And s is equal to minus 3 plus 4i. Anytime you have complex zeros or poles, you're often, in fact, almost always going to get the complex conjugates are both going to be poles or zeros. So there we go. And we just take those values and we come back here to our example. We can come back here and say that we have zeros at s equals minus 5, and then minus 3, minus j4, and minus 3 plus j4. And there we go. There's our zeros. Let's go and do the poles. We'll do them in the exact same way. This time we'll just set the denominator equal to 0. 4 s to the fourth plus 88 times s cubed plus 880 times s squared plus 4,000 s equal to 0. And just like before, we'll go back to Wolfram Alpha and we'll say solve 4 times s raised to the fourth plus 88 times s raised to the third plus 880 times s raised to the second plus 4,000 times s is equal to 0, and we are solving for s. Let's get our solution. All right, here we go. We have s is at minus 10, minus 6, minus 8i, minus 6 plus 8i, and then s equals 0. So let's go ahead and jot that down. We've got our poles now at, say poles at s equals minus 10, minus 6, minus j8, minus 6 plus j8, and at 0. And that is all there is to it. This is how we find the zeros and poles of our Laplace transform functions. Let's go ahead and work out one more example since we've got some time. Example number 2. Gives us this. F of s is equal to 8s squared plus 120s plus 400 over, what do we have? 2s to the fourth plus 20 times s cubed plus 70 times s squared plus 100 times s plus 48. And we need to extend that line. So what I'd like for you to do is go ahead and pause the video right now and try to solve this one on your own. It should be pretty easy. You're just going to plug that numerator and the denominator into Wolfram Alpha, but go ahead and give it a shot. I'll wait. Okay, well, hopefully you worked that out just fine. So I'll finish it out here. Let's go ahead and find the zeros first, like we did last time. It doesn't really matter which one you solve for first. They're both independent of each other. So we have 8s squared plus 120s plus 400 is equal to 0. Now that one's a quadratic, which may be tempting to solve on your own or not. So let's go ahead and solve. 8 times s squared plus 120 times s plus 400 equals 0, solving for s. And we get s is at minus 10 and minus 5. So let's go ahead and jot down that solution. We have zeros at s equals minus 10 and minus 5. Now let's go ahead and find our poles. So we set the denominator 2 times s to the 4th plus 20 times s cubed plus 70 times s squared plus 100 times s plus 48 equal to 0. And we go back to Wolfram Alpha and have that we want to solve for 2 times s to the 4th plus 20 times s cubed plus 70 times s squared plus 100 times s plus 48 is equal to 0, solving for s. And we get minus 4, minus 3, 2, and minus 1. So let's jot those down as our poles. So we have poles at s equals minus 4, minus 3, minus 2, and minus 1. So there we go. That's how we calculate our poles and zeros for our Laplace transform f of s. So now we are actually done with our discussion of the mechanics of the Laplace transform. In the next lesson, we're going to move into chapter 13. We're going to start applying these Laplace transform techniques to our circuit elements and our circuit analysis. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I look forward to seeing you guys in the next lesson. Thank you.